Every single journey tells a story, right? Think about it. A car accelerating onto the highway, a sprinter bursting out of the blocks, even a rocket blasting off. But how do you actually tell that story visually? How can you capture every little change in speed, every shift in direction, all in one simple picture?
I mean, if you try to describe all that motion with just words, it gets super complicated fast. The car went fast, then a bit faster, then slowed down. It's just messy. And a big list of numbers? That's even worse. It doesn't give you that aha moment. You can't see the big picture. We really need a better way to see the entire journey all at once.
All right, so let's get into it. The answer to this problem is this amazing tool that comes straight from physics, and it basically acts like a map, but for a journey. And that map, that answer? It's the velocity time graph. It looks simple, maybe even a little boring at first, but trust me, it's packed with all the information we could ever need.
So let's take a look. The whole setup is actually super intuitive. Up the side, on that vertical y-axis, you've got velocity. And remember, that's not just speed, it's speed and direction. Then, along the bottom, on the horizontal x-axis, that's just time ticking by. Simple as that.
Now here's a really key thing to remember. This graph is specifically for things moving in a straight line, okay? Its whole job, its entire reason for being, is to show you visually how an object's velocity is changing from one second to the next.
Okay, so we've got the basic layout down. Now for the fun part. We're going to learn how to actually read these things, to speak their language, because every single line, every slope, it's all telling a piece of the story. And check this out. This image shows you the 4 basic words in the language of these graphs. See that flat line at the top? That's for steady, uniform motion. The line sloping up? That's speeding up, acceleration. The one sloping down is slowing down, deceleration. And that curve at the bottom? Well, that's when things get a little more complex. That's non-uniform acceleration. For now, let's just focus on the 2 simplest ones. If you see a perfectly flat horizontal line, that means the object is just cruising along at a constant velocity. It's literally like putting a car on cruise control. No speeding up, no slowing down, 0 acceleration. But if you see a straight line that's sloping, well, now the velocity is changing, but at a steady, constant rate. If it's sloping up, that's constant acceleration. If it's sloping down, that's constant deceleration. But here's where it gets really cool. These graphs don't just describe the motion, they let us calculate stuff with amazing precision. This is where we unlock the graph's hidden superpowers. And I'm not kidding, these are the exact tools that engineers and even video game animators use every single day. Okay, superpower number 1. It's hidden in the slope of the line itself. The steepness of that line, it's not just some random angle, it's an exact measurement. What is it? It's the object's acceleration. So acceleration is just how quickly the velocity is changing, right? Well, on this graph, that is exactly what the gradient or the steepness of the line tells you. A really steep line means the velocity is changing fast, so you've got high acceleration. Think of a sports car just launching off the starting line. A flatter slope, that's a much slower, more gentle change. All right, get ready for superpower number 2. And honestly, this one might be even more amazing. So, if the slope is all about acceleration, what about the area underneath the line? What does that tell us? Well, it reveals the displacement. And displacement is just a fancy word for the object's total change in position. Basically, how far it's gone from its starting point and in what direction. And to find it, you just have to calculate the total area squished between the graph's line and the bottom time axis. That's it. So how do we actually do that? Well, check this out. For a journey with different parts, speeding up, cruising, slowing down, we can just break up the area under the graph into simple shapes we know, like rectangles and triangles. Then you just calculate the area of each of those little shapes, add them all up, and bam, you've got the total distance traveled. It's such a clever and simple way to solve what seems like a really complex problem. And this is used everywhere, from designing roller coasters to programming delivery drones. Okay, let's pull all this together. What's the big takeaway here? This stuff isn't just for a physics exam, It is a genuinely powerful way to see and understand the story of motion. And it's used in the real world all the time, from designing the physics in your favorite video game to training astronauts. So, just remember the basics. This one graph tells you pretty much everything. The vertical axis, that's your velocity. The horizontal axis, that's time. The gradient, or the slope of the line, that's your acceleration. And the area underneath it all, that's the displacement, the distance traveled. A flat line means constant speed, and a straight, sloping line means constant acceleration. With just that, you can read the entire story of a journey.
So we've pretty much cracked the code for telling the story of a journey in a straight line. But what happens when things start turning? You know, when the path isn't just forward and back, but also left and right. What kind of map would you need for that kind of journey? Definitely something to chew on.